Can you help me? Sorry, what's this? Thanks. Okay, we can start. Hope it's going well, and if someone can check with YouTube at some point, let me know if it's screening okay. So last time we talked about the double slit experiment, and at the end of the lecture we said we're going to look at the simplest example when it's just in 1D. So we'll recap this and then we'll finish it. And then that's going to be it for the free particle for now. I'll give some more examples, but all very informal. And then we're going to finally see the point where we have a non-zero potential, which is what we'll spend like the next couple of weeks on. And you'll see the simplest possible case, which we call the particle in a box. So I'll explain what this is in a bit. So let's just recap what we did last week. So we talked about the double slit experiment. And in general, what we found out was that if the wave function is a superposition of two waves and there's some phase difference between them, then this phase difference causes the interference. So I'll just write it down. When you have this kind of situation of where the whole wave is something like this, and the wave functions are otherwise similar. Minus some constant L. So that when we have this, where so in this case we had that L was kind of the distance between the two slits, between the average of the two slits, right? We had this, then we have this wave coming from here, this wave coming from there. And then at the end, there's kind of an interference pattern here. And we saw, well, informally, I gave you enough reason to believe that the square of the wave function at the end is going to be something like this, right? So again, so from this phase here, and we saw that as we change the phase, this causes an interference pattern. In the sense that if I call this total wave function that depends on, sorry, on this phase, and the square root of the wave function look like something like this, right? At some point. And where did this phase difference come from? It came from like the distance between the two slits compared to K. Right? This we derived rigorously. What we did not derive was exactly this thing here. Okay, so this is what we're going to see. So how do we observe this? One, we do the full calculation, right? This is what we will not do. There's one approximation of the full calculation in the lecture notes, the typed ones. It's called the stationary wave approximation because we need to evolve these two waves until a certain point, and then try to find a time-independent solution and so on. It's a bit much. Yeah. Good. Or the second thing that we're going to do now, which is to take, instead of having these two waves there, we take two waves coming together directly. And why will this give us the right solution? Because look, the interference is always there as soon as there's a phase. We just need to make kind of the envelopes of the two wave functions overlap so that we can see it. So the easiest way to make them overlap is to just send them one against the other. So we'll see what this is. So we see what happens when they both reach here. So in principle, we'd have the one from the left here and the one from the right there. And then we're going to see what the interference is there. And then we saw that we can approximate the Hamiltonian. Just p squared over 2 mu. We said, well, we can approximate this by one term that is linear in momentum operator and a term that is just a constant. When is this approximation good? Well, it's good when first the mass needs to be large, much larger than all other constants here. And second, we choose for P0 being the initial P of the wave function, right? So this is what we did last time. Now note that, for example, if we have a wave moving here, then if we want to look at what the approximation is for this part of the wave function, then it's going to correspond to the P0 that is going in this direction, so positive. But if you're doing it here, the right approximation is the one that goes in this direction. Okay. And then, I mean, of course, this is an approximation, so none of the results will be rigorous, but we can rigorously bound. We can bound the difference between this operator and this one, and we could do the whole calculations to see how far our actual result is from the from our approximation, right? Okay, and the key thing here is that then we have h bar for a wave function with P0 going in with a given P0. This is going to be E at T h bar. Right, to do this, this is the exponential that comes from this part times A IT P0 over mu. And this is good because this is just a global phase. We'll see. And this is just a modular momentum, right? This is of the form e to minus I and we know that this acts on the wave function. On the position wave function like this, which will make the evolution very easy. So this will become more clear when we look at an example. So like, let's just show how it looks in general. If you have a wave function with a kind of a well-defined momentum initially, and you want to evolve it, did I call it phi? So phi is this phase. This is the first part. And then we have the second part. And we apply this on the state, and we can expand the state in the position basis. So x and time equals 0. X. So EIT check. And then we know how the momentum acts on the wave function. It's exactly as I said there. So you get of x minus 0 over mu times t x, right? And this, just so we don't write, just so we don't write this all the time, p0 over mu, we just call this v0, right? It's momentum divided by the mass, has the same units as velocity, we call it v0. Yeah. Okay. But now we want to apply this to a specific state, and then it gets a little bit more subtle. So what's our initial state? Like I said, and really think of like shooting electrons one against the other. For example, so we have phi L plus, right? And in fact, even with phase equals 0, unless you're very unlucky with the K's and L's, you can already see the interference. But we can see what happens if you have a little phase here. Let's say alpha, so you don't confuse it with the other one. So then we call this, say, alpha of 10%. And what do we want of these things? Well, we want that psi L of x, this is a Gaussian that is at the moment, well, for symmetry, we're going to put them at L over 2 and minus L over 2. This will be useful later. So we have a Gaussian that's here, moving with momentum k, and we have a Gaussian that's there, moving with momentum k, minus k. So what's this? Well, EIKX, and now we have of x plus L over 2, where just write it instead. Use just the Gaussian. Sigma squared. So if I have this, I have a Gaussian envelope centered around here and moving in this direction. Whereas for the other one, I want it moving in the opposite direction. And centered around plus L over 2. So far, so good. So now, comes the subtle part. So what's V0 for this wave function? Well, this is going to be the average of P for this psi L divided by mass. And that's H bar over mu. We call this, let's call this V. In the lecture notes that I'll upload today, I call it V0, but just so we don't write the 0 all the time. So we just call this V. For this one, V0 right, same thing. And that's minus K. So that's minus v here, right? Which means what? That, you know, if you think about the Hamiltonian here, we think that the mass is very large. How is the Hamiltonian felt in this region? Well, it's this approximation with your P0 being kh bar. How is it felt here? It's the same approximation, but with P0 felt minus kh bar. If you use the same P, if you use the same V0 equals V for both waves, then the approximation will be very bad in this way because it's really moving with the opposite direction. So I'll just write it here how it is. So just read this as like the Hamiltonian S felt by the particle here is approximately V0p minus, and now it's V0 squared over 2 identity. I did just that thing there, just replaced P0 over mu by P0, right? So it's exactly that. And V0 I called now V, so let's call it just V. For the right, get minus Vp, and then minus here V squared, minus V squared is the same as V squared, so this. So you get the same constant here, which means that you'll get the same global phase, and this is important. Okay, so by L of t is approximately e to I phi t, is that right? E to I phi t, and e to minus I v t h bar p L. E to minus I plus I v t. So this is a dodgy part of the approximation, is that we're not using the same approximate Hamiltonian for the two parts, for the two wave functions. But this is the one approximation that makes the full evolution right. And if you want, you can go through the trouble of doing the whole thing. So now we just evolve the state, and then we kind of torture the formulas until they show us what we want. And again, the reason we're doing this is that interference has so many applications. And you should see at least one example explicitly of really seeing it emerge. And this is the one with the simplest calculations I could find. It doesn't mean it's prettiest. So then after time t, it's going to be 1 over square root of 2 of L of t plus E eta. Trying to see how I make this the least horrible. Okay, they have the same phase, right? So we put 1 over square root of 2 e to I phi t, that's what I wrote there. And then we have E2 minus IV. There we go. Okay. So now we just replace with the wave functions there. So we get a big integral, 1 over square root of 2 e to I tech t. And well, actually, let's make a trick. No, we do the trick after. Let's do this properly. So minus infinity to plus infinity, dx, x. And now what comes in here? E, I, k. So it's the initial wave function, everything just shifted by vt. So we have x minus vt for the left. And the Gaussian at the position with this TV plus this L over 2 that was there before, right? So where I take the original wave function, wherever it was x, I put x minus TV. Plus e to I alpha. And now e, k, again. X plus, for the right I do plus TV minus L over 2. And now let me see if all the signs are okay. Are all the signs okay, or did I mess up something? No, this has got to be a plus. No? Okay, let's see later what this sign here is here, okay? It might be a plus or a minus, I need to see. Okay, now we do the trick of, we have this phase here. And we want to multiply everything by E I alpha over 2. So then we have here E minus I alpha over 2. And here we just have I alpha over 2. Okay. This is going to make things easier later on. Right now it's like, why would you do this? But now we replace the wave function, the Gaussian package of the wave function with the actual Gaussian that's up there. And it's going to get a bit more horrible because before it gets nice. So I have 1 over square root of 2 e to I t e to I alpha over 2. And then now this constant that's there at the beginning of the Gaussian is the same for both of them. So you have square root 4 of 2 pi sigma squared. The x, And now let's see what's here. So if E I K X minus VT minus alpha over 2. And now comes the part from the Gaussian, so it's E of minus X minus the new X0 is TV plus L over 2 squared or sigma squared. This is the contribution from the left plus minus IK So I need this to be a 0. So this goes inside here, there's a minus sign. I want to put everything inside brackets with the minus sign, so I get a minus there. And then I need this to be V. E minus X plus TV minus L over 2. Okay, this is quite terrible, but now we're going to simplify it because remember what I said, we choose the moment when they're both in the center. Okay? So you're going to choose a particular t. Which is the moment it takes for each of them to cover the distance L over 2 so that they're in the center. So it's the distance L over 2 divided by the speed. So what happens is that at this point, both of them are, these two terms cancel each other. So both of them are centered at x equals 0. So at this point, then we have, well, let me just write it at position x, and for time t equals L over 2v. So this just means I'm just looking now at the wave function, not at the whole state. So we get rid of this integral and x, and we're looking just at everything that's inside. We have this massive constant that we don't want to write all the time, so let's call this A. And now let's call this thing here B. Okay, the same as here. So then we have A, and then we have two terms. So e to the IB times E minus x squared over 4 sigma squared plus E2 minus IB E2 minus x squared over 4 sigma squared. Okay, good. So now this is starting to look more treatable. Okay, so this thing is the same in both terms, so we plug it out. So we have A E2 minus x squared over 4 sigma squared. And now we have E2IB plus D2 minus IB. And now if you remember your trigonometry, if you divide by 2, this is a cosine. So now we just multiply it by 2 outside. There you go. Okay. So this is now 2a my Gaussian envelope minus x squared over, oh, stop, 4 sigma squared. And now we have cosine of B. And what was B? B was that thing. We rearrange terms so that it's a bit neater. So it's K. And let's put it x minus BT minus alpha over 2K. I just put it like this because then it's easier to draw. Okay, so we finally evolved. We find a point where the wave function looks like a cosine, which means that the square of the wave function is going to be like look like a cosine square. And the only thing I'm not sure about is where is that minus sign over there at the beginning, how we got it. Okay. So then what we have for the square of the wave function? For this special time. It is now 4 a squared e to the square of that is just replacing the 4 with a 2 sigma square. And then we have cosine squared of that whole thing. Okay. And now we can go back to what A was, right? A was that whole thing. And you can plug it here and see what we get. And it should be something like 2 over pi sigma minus x squared by 2 sigma squared x minus L over 2. So how does this look like if we plot it? So this is the position. First we draw the envelope, that's this part here. This is just a Gaussian. Should be centered around 0. And now this thing is cosine of kx, but shifted by this amount, right? So there'll be some amount here, which is, there's some amount here that is L over 2 plus alpha over 2k, which is where we see the first peak. And then it looks like k square, right? And the wavelength is this, right? Because it's k square. Sorry, it's cosine square. So if you looked at the whole wave, cosine has 1 period while cosine square has 2. So this is the whole wavelength is 2 pi over k. So how do we measure this? In the lab, 2 electrons or 2 atoms sending against each other at this precise time, measure the position. And you get something here. And then do it again with 2 new electrons, tack, 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 tack. And then overall you measure statistics that should be coherent with this plot, right? And so from where you see the most electrons, which would be around this area, you can deduct what the phase was. And you know, if you knew what the phase was, you can deduct what the initial distance between them was, and vice versa. So in this case, if you don't know the distance, you don't know when to measure. That's okay. Okay, so this is the interference example. And now I can tell you something like an application that I learned about last Thursday. We went to see a lab. Yes? So it's the time that it takes for, so you have distance L between them. It's moving with velocity V. So it's the time it takes to. Sorry? V is the V0, yes. So V0 is the P of this one at time 0 divided by mu, which you can think of as like the velocity of this wave at this time. Sorry? This, you can define an observable called V. It's just P divided by mu. It's a bit tricky to make like direct connections between the quantum case and the classical velocity, because you have the velocity of the whole wave, then you also have like the velocity of like the little oscillations within the wave. But maybe the simplest way of saying why we choose this T is because at a time that's nice that this like the Gaussians kind of look like the same, right? The center of the Gaussian travels at this speed, which is why we call it the velocity group. Sorry? It has us, yes. Yes, yeah. But in this case, we're interested in making this kind of the envelopes. So that it fits, and to have the one here and the other one there, so that we can see the interference, right? So then we choose T such that the middle of the Gaussian will be there. For this approximate Hamiltonian, that's approximately directed with P and not with P squared. If you add P squared, then it gets a bit more complicated. But still, we saw that X at times T is going to be X0 plus P over mu T. So you could do this for each of the halves, right? You could do this for the left one and for the right, and this is what we called V0. Yes, it's constant, yeah. Yeah. Yes. Okay. So maybe before the break, so after the break, we changed topic completely. Maybe just before the break, I'll give you more examples of how interference is used. Now that you've seen like the basics of one example where you see it really emerge. So I went to a lab of hybrid quantum systems. This is by Professor Yuan Chu, and we got a tour of the lab with this teenager that was with me last week. And what they do is they use lasers to see sound. So more precisely, they have a little crystal of doesn't look like this. They have a little quartz crystal, kind of the size of a fat coin. I think 11 millimeters or 12 millimeters, like this. And what they do is they produce sound waves inside, and sound is just, the air in the air is air compressing and expanding. In the crystal is the crystal compressing and expanding, right? So you can think that at some point you have areas that are more dense and areas that are less dense. they cooled everything to just a few Kelvin, and they want to cool it down to a few millikelvin so that there's not a lot of noise. So, the change in density in the crystal is really just from this wave sound that's traveling inside here. Then they shoot a laser at it. And then depending on the density of the crystal, the laser is refracted differently. Right, so think of light going through a glass of water, or think of just light going through like a fat glass window, right? It's refracted, and the refraction index depends on the density of this. So in principle, it should be sensitive to this. Okay. So it results in a very, very small shift in the wave, so either in the frequency of the light or so on. Then so this laser comes out, and then they interfere it with a bigger laser that's kind of massive laser there, little laser here, and then they have some detectors. And then there's some clever procedures called Homodyne Detection that can see the interference of this light here with this light there. From this interference pattern, you can determine what the shift was here. So you can determine how dense the material was. So you can actually kind of map the light in the whole crystal. Sorry, you can map the sound in the whole crystal, right? Which is not an example you'd originally think of this. I also did an experiment once where we have like a little mercury ball that was oscillating with sound. So we had a speaker pointing at it, and it oscillates. And it should have something like the resonance frequency in which it oscillates more, right? So it means that this surface here is moving up and down. And then there's some devices called Doppler Interferometers, which what they do is exactly, they shoot a laser in this direction, the laser gets reflected. And then depending on like the oscillation here, there'll be a phase difference between the incoming and outcoming beams. They interfere it. And then from here, they deduct like how fast it was vibrating there. Yeah. This was an experiment that we did for 0G flights. So the European Space Agency had this project where they have these airplanes, very well padded, and they send them, essentially they accelerate them, and then they'll turn off everything, let go. So you're kind of floating inside in free fall. So you're meant to propose experiments that work in 0G. So we proposed this because we think, oh, then this like little mercury ball is perfectly spherical because it doesn't feel gravity and so on. Of course, the experiment didn't work because the whole plane was shaking. This was inside the glass window, it was shaking. The laser felt all of this vibration, so it ended up not measuring anything relevant. But it's again an example of how this little laser, interference experiments have many, many, many applications. Okay, so maybe I'll let you go for a break now. We start at 10 past. And then we'll talk about a completely different topic. Thanks. Okay. So then let's see. Let's first recap on some tools that we learned a long time ago, and then I'll tell you what kind of examples we'll do and what we'll do today. So I don't know if you remember that we talked that we have these Hamiltonians of this general form plus x, write it like this. And what did we say? Well, in general, for any Hamiltonian, we can find what is called the stationary states. These are the energy eigenstates, right? So these are the ones that have the eigenstates of the Hamiltonian with some eigenvalue E, which we said corresponds to their energy. And we saw that if we want to evolve this was really a long time ago in time. This is just a phase, is E to minus I E T over H bar. And then we saw, okay, so now if you want to evolve some arbitrary state, so if you have any state, we can always expand it in this basis. So sum over all E or integrals if this is continuous, but it's not going to be. Then after time t, everything is linear, so this evolves just to a superposition of E I T over H bar. So whenever we want to solve a system, if we can, we find the eigenstates of the Hamiltonian. This is not always easy. In fact, it can be NP hard to find it. But then once we have them, then we just evolve them individually, and then to compute the evolution of an arbitrary state is just a superposition of these evolutions, right? So this is general procedure. Now, what kind of potentials are we going to look here? So just as an overview, we're going to look at things called the potential wall. So this is E of x, and this is x. So you can think, for example, of your particle being confined here because, I don't know, maybe it's an electron, it reacts to the electric field, and you really raise the electric field around this region, okay? That it's kind of confined here, and we're going to see what happens in this case. Or this is called the potential well, or things like what is called the double well, where maybe looks like this. So this is V of x. And again, so there's some region where it's very high, and you can think of it like some wall, and then you have a particle here, and then we'll see the phenomenon that's known as quantum tunneling, which is when there's a small probability that you'll find the particle on the other side when it should not be there. In terms of applications, like a lot that goes on in quantum devices labs is like really trying to get very fine control of these potentials and seeing what happens to electrons and other particles here in order to build everything from, transistors to qubits to, these days a lot goes into trying to make a quantum computer. So trying to make something like, for example, this would be corresponding to state 0 and this corresponding to state 1 of a qubit or so on. Or quantum sensors, or we'll see once we see specific examples how it looks like. But today we just do a warm-up for this. So today we do what is called the particle in a box. This is a warm-up in which, let's say here is 0, here's L, and your potential we just make it infinite outside this region and 0 in the region. Okay? So it just goes like this. Now, this is a completely unphysical example because you can never make infinite energy, but it's going to be useful because we'll find some properties here that then we can approximate in this case. Good, so let's do it. So our v of x, it's going to be 0 if x is in this region and infinite otherwise. Okay. Now, again, this is totally unreasonable, not just because it's in infinity here, but because it's such an abrupt change. But we do a trick by imposing some boundary conditions. So we say that, well, if wherever f of x equals infinity, our wave function needs to be 0. And in particular, in this region here, and this point here, it needs to always be 0. So you're going to think of the wave function as something that is 0, 0, 0, 0. Here it's allowed to do whatever, and then 0, 0, 0, 0. So of 0 times t this is kind of to make the math work out and for us to justify this a little bit. Okay, so now what's the first step? We look for the stationary states that are the eigenvalues of this Hamiltonian. And we're going to make an educated guess, right? By which I mean, I'll give you the solution and then we'll see that it does work out. Yeah. But just think of it as like, think maybe of a guitar string that needs to be at position 0 here at 0 and at L, right? So these are the two extremes of your guitar and needs to be here and here. So what kind of nice waves can it have? Well, one could be something like this, or another one, something like this, or going around once more, one more oscillation. So in general, at wave functions of the form a sine of kx, sine because sine of 0 is 0, but then it needs to satisfy the boundary condition, so it cannot just have any wavelength. So we need that of L. This is a sine of KL, which means we need to look for values of K such that sine of KL is 0. And this is so for all n that are natural numbers, if your k is of this form, then when we get here, so you have kl, so you get just n pi, and sine of pi is 0, right? Sine is vertically, this is 0, this is pi, here it's 0, here it's 1, here it's 0 again. which means what? We're going to get this. We're going to get this solution. So check. This would be n equals 3. This is n equals 2. And this one is n equals 1, the yellow one. So I've not yet proven anything. So maybe we should do that. So the claim is that psi n of x and sorry, I'll just write here kn. That's with kn rule pi n over L. So the claim is that these wave functions are eigenstates of our Hamiltonian. Okay, so then now we need to prove this. So we need to see what happens to H psi n, right? Okay, so inside the box, what we have is just a free Hamiltonian. Right. So then we can see, so inside the box we have this. Well, maybe it's easier if let me do the whole thing. So H n equals H dx x, right? Now, because both H and psi of x are 0 for x not being in this interval, so you could expand this into into 3 terms, to the left, in the middle, to the right, but the left and the right are always going to be 0. So then what's surviving is inside the box. We have from 0 to L, the x p squared over 2 mu psi n of x. Okay. And we want to see what happens to the position wave function, so we put an x here. Let's say x prime. So we're going to see what happens to this thing. Okay. This we computed a few weeks ago, if you remember. H bar squared n of x minus h bar squared x squared. And now what we have here, just replace here a sine of kx, yeah, x. And now what's the derivative of the sign? Is the cosine or minus the cosine. If you derive it again, you get minus sign. So you get h bar square, n squared, a minus sin of k and x, which is h bar square, kn squared, check, and x. In this here, well, now if we put the two mu under everything, and this is the an. So the conclusion is h psi n equals n psi n with n being h pi square, 2 mu, and kn we can replace already with it. Well, let's put here kn squared, h pi square, 2 mu, n squared, pi squared, l squared. So you can rearrange this a bit. And square. So this first term here, this is just this thing when n equals 1. So I can just call this E1, this whole thing. So it's E1 n square. So what have we done? We've shown that these wave functions are eigenstates of the Hamiltonian by looking at how it acts on the wave function and showing that, well, inside the box, it gives a fixed multiple of the wave function. Outside the box, it's always going to be 0, but so it was before. The only thing we don't know yet is this constant A, and the constant A will come just from normalization, right? Because you need the whole wave function to be normalized. I'll leave this here. Okay. So how do we find so far? Finding this constant A. Well, you know that the wave function needs to be normalized, so is it A to plus infinity? This needs to be 1. Of course, this thing is 0 outside the box, so you just need to care about the integral from 0 to L. And then we have A squared X. And now I don't know if I'll ask you to do this in a tutorial, but or you did this in calculus 1. But this is like a standard integral. We don't worry about it for now. And it gives this. So we conclude that the wave function of x is constant 2 over L sine of this Kn, which was pi over L n x. Good. So now, how do we care about time evolution? So now if we have some, yes? Yeah.
So we found out that the eigenstates are here divided to 2, but we have a continuous system.
That's the thing, then n is not continuous. Yeah, okay, so yeah, maybe I should have remarked more on this. So now we have the following eigenstates. So the eigenstates of this Hamiltonian, even though position is continuous, they are not continuous, they're discrete. And and one can show that these are actually the only eigenstates of the thing. And they look like this. So if I put here, this is x, and here I kind of map them. So this is the first one, which is, if I map here, kind of the energy, right? It's 0. This is E1. Then at 4 E1, you have the second one, which looks like this. Then at, how much is 3 squared? 9. E1, you have the third one, which is this, and so on. So indeed, and this is quite a special thing. And in fact, I mean, the whole world, the word quantum just means bit or discrete bit, and it comes from this. And this was what puzzled scientists when they first discovered quantum mechanics, is that you expect everything to be continuous, but in fact, the energy eigenstates are discrete. I think most of them are going to be 0, but let me come back to this on Thursday then. Yeah, it's a good question. I'm not entirely sure. But they do turn out to be like this. I mean, in the same way that you can do this again with the guitar. If you trickle it, if you like flick it and you look for stationary solutions, they're going to be of this form. Now, if you want to evolve any arbitrary state, then we just have to do this, right? But now in this case, now we know what this is. So if you have some initial state, let's say 0, which is a sum over n. You know, it's going to evolve to E2 minus E1 n squared time so we're going to look at a very simple example of this. So now it's similar to when we did this example of a spin rotating. So we're going to start in a superposition of the first two. Depending on time a minute. Lots of time. We're going to start, say, prepare my little particle in a superposition of the first two energy eigenstates and see what happens to it. And what we'll see is that it kind of bounces from one side of the box to the other, like boom, 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 boom. So let's do an example. So again, like in
Question: the summing over n, is it the same n as the quantization of the energy, or is it?
Yes, it's exactly the same. Yes. So I'm summing over all the energy eigenvalues, which is the same as summing over all n, because En, I already raised it. En is just E1 times n squared, right? Yes. Yeah.
Why is the greatest n equals 0 not making us?
Indeed, but then it's a very boring solution because it's just no, it's not normalizable. If it's constant, you cannot normalize it. So it's just going to be 0. So yeah. No, that's not true. Yeah, it has to be 0 at the endpoints. It needs to be constant, so it needs to be 0. Yeah. If it was a roll space, it's not normalizable. Here, it has that extra problem. Yeah. Yeah. Okay. So now we're going to do an example where we just have two. So we have that general case, but we just take two parcels because it is simple. Okay, so let's say phi of 0 time equals 0. And we take the coefficients to be the same, again, because it will simplify calculations later on. Okay. So let's say like this. So these are different values of n, L and M. And let's just call m squared minus L squared. We call this delta, which is a natural number, right? So let's say we pick m larger than L, and then we do this. Okay. So this is a less energy, more energy here. Eigenstate. Okay, so then we have what? T. It's 1 over square root of 2 of E minus IT E1 H bar L squared plus, sorry, L E minus IT E1 H bar M squared. And now, because L is smaller than M, we take this L out. So we have 1 over square root of 2 E minus IT E1 H bar squared. So that then we have L plus and now we have here m squared minus L squared, which is just here delta. So again, it's like the other case before. We have some global phase that will not matter for measurements. And then inside we have a relative phase plus E minus IT1 delta. So same thing as before. We have a superposition of two wave functions with a relative phase. The relative phase depends on L and M. The difference is that now these are not the same wave functions as before. They're not this like fast oscillating Gaussians. Instead, these kind of things, right? So then this changes the picture a bit. Okay. So we'll see how it looks exactly. We're going to replace this with exact wave functions. So we have, looking at the wave function, not the state. I forgot the H bar. H bar. Sine of X. What I did was to already use the A equals square root of 2 over L to get rid of the square root of 2, and the L is there. Is that okay? Okay. So now let's see the square of this. And this is like we did before for the double slit in general and all these interference examples. In general, this is the phase goes away. So we have one over. And then we have all these different terms. So we have one that's going to be sine squared. This is the contribution just from, this is proportional to just squared, right? This is just from the L plus the one that comes just from the right, M X over L. Okay, so this is proportional to up to constants by M of X squared, and then you get the two cross terms. Which again, so think that it's, these are real numbers, right? So maybe I'll do it here in small just to show you where it comes from. Let me do it here. So if this first sign is A, is a real number, plus E to Y something, B, which is a real number, So we need to do the square of this, which is this, plus AB e2 minus I. Right? Because we're not just doing the square, we're doing the modulus square. But A and B are real, so they don't change. But you have these two terms with a different sign, and it's the same trick as we did in the first lecture. So this is going to be 2 times cosine of alpha AB. Is that? Is that clear? So that's just what the interference part looks like in this case. So you get 2 cosine of alpha is this thing, T delta E1 over H bar, multiplied by the 2 signs, by A and B, so these are these 2 signs, times sine of and here you can remember, look, this is the wave function L on system X, and this is proportional to the wave function M. And it's modulated by something that depends on time. Look, time only appears in this whole thing, only appears in this term here. So now we can plug this into a computer. And make a nice simulation of what it looks like. If you evolve it over time. And my drawings are not as nice as the computer, but I can try it. So in the simplest case, where you just have a superposition of the first and the second eigenstate. So if M equals 2, L equals 1, then the way this looks so some t and time evolves in frames, okay? So this is at some time later, much later. And this is the box, so this is X. So at some time, it looks like this. Then later on, it looks like this. Then later on, it looks like more on the right. Which means what? If I measure the position at this point, I'm more likely to find the particle around here. If I measure at this point, it's anyone's guess. And if I measure here, then I'm more likely to find it there. And then it goes back. So this is time. And then it goes back to this kind of thing, right? Because it's a cyclical thing. You can see from the, you have a cosine of time times something, so everything is cyclical. And in this case, it looks exactly like this, like the particle being mostly here, mostly on the right, and bouncing back and forth. Okay. We can approximate this in the lab by, again, taking a particle, cooling it really down a lot so that it becomes mostly a superposition of these two states. It's much more complicated than this. Good, so this was our simplest toy example. And here's finally a case where the quantum case is very different from the classical one, in that indeed, like the energy levels are discrete, not continuous. And if you see any kind of movement, it comes from this from evolution of the superpositions of the eigenstates. And the process is exactly the same as for the interference case, but because the waves look differently, then the interference looks different. Good. In the next lecture, we're going to start with finite potentials. I'll give you the general thing, and I think I still have this extra lecture that I should record at some point. And because the next few lectures are going to be kind of all the same, it's always the same procedure. We do first a box like this, then we do a box like this, then we do a box I might record one of these instead of doing it in person. And then do this in person. Very good. Okay, I'll release you now. Enjoy lunch. See you on Thursday.